Today we will discuss the ripple factor of the pi filter. Okay. You know what is first of all, what about the circuit diagram? In the circuit diagram, it is shown there is a step down transformer. This is the primary of the transformer, and where we can give our supply like 230 volt, 220 volt, or maybe else with 50 Hz frequency. So AC is applied between the 2 points. You know what the function of this rectifier as well as the filter circuit is to convert AC into the DC. So for this conversion AC to DC, there is a transformer. Now these two lines shows the iron core. Okay. Now this one is the secondary coil. At one end of the secondary coil, there is one diode is connected, and at the second end of the secondary coil, there is a second diode which is connected. This is central tapping, you know, because from the center of the secondary, and it is also at earth potential, the output is taken across this grounded line and this line, you know. Now this is P, this is N. Likewise, this is P and this one is N. N of both the diodes are connected together. Okay. And then output is taken from this line, which is common end of both the diodes, and from the central line, which is grounded, central tapping to the transformer. Now then we are having a filter circuit. Now function of this circuit is, okay, conversion of this type of AC. This is the applied AC, and this circuit will give us unidirectional, and unidirectional means it is varying in one direction, but still this is a pulsating voltage. This is not exactly DC. So it is still there are fluctuations, but are present only in one direction. So AC was bidirectional. Now output of the rectifier is unidirectional, but still pulsating. Then we are having the filter circuit, the capacitor C1, C2, and the coil. This shape is like, you know, this like a pi. So that's why it is called the pi filter. And output is taken between the two ends, where a resistance RL is connected, right? So this simple diagram. Capability of this filter circuit is very, very good in comparison with that shunt capacitor filter or series inductor filter or LC filter. So pi filter is good for ripple rejections. Now just look, this is our filter, you know. This is half wave, this one is the full wave. If you are not using the filter circuit, okay, if you are not using the filter circuit, then you will get either half wave if we are using one diode, And full wave if we are using 2 diodes or the 4 diodes like a bridge circuit. Now then, if you are using only one capacitor, means shunt capacitor filter, then if the half wave rectifier, then you will get the output like this. Then the average DC will be from this to this line. This will be the average value, mean DC value. This will be the DC value from here to here, right? If we are using the pi filter, then you will get like this. Now the average value, now it is increased in half wave. Now if we are using full wave and you are using only one capacitor, then you will get like this. And if we are using the pi filter, then ripple is very much reduced and average value is increased. So it is good, it is beneficial that using the pi filter with full wave rectifier, either by using 2 diodes or by using the 4 diodes like a bridge. Now this is output from the capacitor filter, okay, charging and discharging of the capacitor. This one is output from the rectifier. Along this side it is theta. Theta means omega t, because omega is d theta by dt. So omega t becomes theta. Along this side it is the output voltage. So because the capacitor having property charging and the discharging, so that's why we get output like this. Okay, output like this. Now the ripple factor will be from here to here. This is a ripple variation. Okay, this is not the pure DC, still it is fluctuating. So ripple variation magnitude is from here to here. What is the value of the ripple? This is the expression IDC over 2FC1. So for this derivation, that how it comes, so please you go to the link which is given here in the description box. Now this is our filter circuit, pi filter, okay, C1, C2 and L. Now assuming that we are assuming this approximation, that we are assuming the ripple shape is triangular. Triangular is like this. So this is our approximation because the output is not triangular exactly, but for convenience we are assuming the ripples, they are triangular in shape. Okay, so we can apply the Fourier analysis if it is some triangular shape. The Fourier analysis tells us that the output will be mixed. Output will be mixed. like having some DC part, this is DC, and because this is sine term, sine mean sinusoidal, and what is the frequency? 2 omega. Again sinusoidal, frequency 4 omega. Sinusoidal, frequency 6 omega. Fourier analysis tells us output contains DC as well as the AC components. AC components of different frequency, 2 omega, 4 omega, 6 omega, and like that, so on. Now, we are neglecting the higher terms, higher harmonic, sorry. We are neglecting this one because of the smaller magnitudes. And we'll consider only the first two terms. So VC1 means output from the capacitor C1. So output from the capacitor C1 is DC as well as the AC. AC of frequency 2 omega. And this is amplitude of the ripple upon pi. And I already explained how this expression comes. So please go to the link which is given in the description box. Now substituting the value of VR here. Substituting the value of VR. Okay. Now we get this value. You know, this is totally pure DC. Now here it is sinusoidal, and this is the peak value. Okay, this is the peak value with the sinusoidal functions. This is the peak value of the sinusoidal mean AC components. AC components. So VAC RMS across the capacitor C1. This is the peak value, you know. And you know the reactance XC1. Reactance is, otherwise it is 1 over C omega. But the frequency is here 2 omega. So that's why it is XC1 means reactance of the capacitor. 1 over 2 omega C1. So XC1 becomes omega is 2 pi F. So this is XC1. Okay. And pi FC1 substituting it here. So VAC RMS across C1 becomes this expression. Okay. So this is the RMS value of AC across C1. So output across here, it is under root 2 IDC XC1. This is the output across the 2 points. Okay, and you know, this is our AC voltage. And you know, this voltage is RMS because here it is the peak value is divided by root 2. When you divide the peak value by root 2, you will get the RMS value. So this RMS voltage is there between the 2 points. This voltage will produce a current in the closed loop. By Ohm's law, we will find that current. By Ohm's law, the current is I equals to, because voltage is at here, and that voltage divided by the reactance of this and the reactance of this. So the voltage across here, VC1, reactance of L1 is XL1, reactance of C2 is XC2. Now, after getting the current, what will be the voltage across these 2 points? Again, applying the Ohm's law. That is current, current which is flowing multiplied by the reactance of C2, that is XC2. So substituting I here, and we'll get VC2, mean voltage across C2, the RMS voltage across C2. So the RMS voltage across C2. So current into XC2. So this output ripple voltage, it is now across C2. Substituting the values of VC1 here, so we'll get VC2. So the RMS value of AC, which is across this OP, mean at the output, right? Now substituting the value of reactances, because XL1, now again assumption. What is the assumption? That XL1 is very much greater than XC2. Then XC2 may be neglected. XC2 may be neglected. So substituting the values, okay, and substituting the value of reactances. So gamma, which is the ripple factor, that is RMS value of AC over DC. So DC is taken to left hand side. Ultimately the expression becomes like this. It's a very important expression. Now this is the last expression of the ripple factor for the pi filter. Okay. Just I am concluding. The pi filter is first of all one capacitor, then a coil, then coil mean inductor, then another capacitor. You know that capacitor always having a reactance, which is 1 over C omega or 2 omega, because in our case it was 2 omega. Like 2 omega mean 2 pi f. So if when the input comes here, which is having AC and DC values. Now for DC frequency is 0 and 1 over 0 mean infinite. So the capacitor offers infinite reactance to DC. So DC cannot pass through the capacitor, right? So DC cannot pass. So DC flows now to the inductor. But AC can pass through the capacitor. But AC of high frequencies can easily pass, but not the low frequencies. The low frequencies needs a more reactance. If the frequency is high, like 4 omega, 6 omega and higher, they can pass through the capacitor. But low frequencies finds some difficulty, because if F is greater, reactance will be less. So higher harmonics will be grounded, but the lower frequencies cannot pass through capacitor, so they goes to inductor. Now inductor again having the frequency like L omega. Mean if the omega is 0, mean frequency is 0, again the DC will pass through the coil, but the AC will find a opposition. So coil also removes the fluctuations, because it allows the DC to pass, not the AC. But even then if some component of AC reaches to the second capacitor, now then we are again having a capacitor. It again allows the frequencies, high frequencies, to grounded and for DC to next appear across the load. In this way, the pi filter circuit works.